Imagine you're given n binary strings, each of length n. For example, 0, 1, 10. And the interviewer asks, construct any binary string of length n that is not in this list. First, this seems trivial. Just try random strings, right? But here's the catch. If n equals 16, there are 65,536 possible strings. Brute forcing suddenly becomes messy. But there's a beautiful trick, a famous mathematical idea used by George Cantor. And once you see it, you can generate a guaranteed unique string in just one pass. Let's dive in. Example walkthrough. Suppose the input is 0, 1, 1, 0. All possible binary strings of length 2 are 0, 0, 0, 1, 1, 0, 1, 1. Two strings are already taken. 0, 1, 1, 0. That leaves two remaining valid answers, 0, 0, or 11. So the answer could be either one. But we want a method that always works, even for large values of n. Let's try the brute force approach. One simple idea is, Step 1. Generate all binary strings of length n. Step 2. Store the given strings inside a set. Step 3. Return the first string that is not in the set. But there's a problem. Generating all possible strings requires 2 to the power of n, and that number grows extremely fast. Even though the constraints here are small, interviewers usually expect something more elegant. This problem is a direct application of Cantor's diagonal argument. The idea is simple. Construct a string where the ith character differs from the ith string's ith character. For example, suppose nums equals 0, 1, 10. Take the diagonal elements. Nums 0, 0 equals 0. Nums 1, 1 equals 0. Now flip them. 1, 1. Constructed string 11. Why does this work? Because the new string differs from every string at least at one position. Matrix view. Nums equals 0, 1, 1, 0. Take diagonal 0, 0. Flip bits 1, 1. Result 11. Check. 11 is not equal to 0, 1. 11 is not equal to 10. Guaranteed unique. For every index I, our string differs from nums I at position I. Therefore, new underscore string is not equal to nums I for all I. So it cannot match any string in the list. This is a mathematical guarantee. Here is the Python solution using Cantor's diagonal trick. We define a class called solution. Def find different binary string takes nums as input. First, get n the length of nums. Initialize an empty list called result. Now iterate over each index I from 0 to n-1. If nums I equals 0, append 1 to result. Otherwise, append 0 to result. After the loop, join the result list into a string and return it. This generates a binary string that differs from every string in nums at the diagonal positions, guaranteeing uniqueness. Code breakdown. Step 1. Determine the size of the input. N equals len of nums, which is the number of strings. Step 2. Build the result. Initialize an empty list called result. We will construct the new binary string here. Step 3. Flip the diagonal bit. If nums I equals 0, append 1 to result. Otherwise, append 0. This guarantees that the new string differs from the ith string. Step 4. Join the characters and return the final binary string. Complexity analysis. Time complexity is O of n, because we only make one pass through the strings. Space complexity is also O of n, to store the result string. This is far better than the 2 to the power of n brute force approach. Common beginner mistakes. First, trying to generate all binary strings. Second, using recursion or backtracking unnecessarily. Third, not realizing the guaranteed uniqueness property. The diagonal trick solves everything instantly. Pause the video and try this example yourself. Suppose nums equals 111, 0, 11, 0, 0, 1. Take the diagonal elements 1, 1, 1. Now flip them 0, 0, 0. The answer is 0, 0, 0. and it is guaranteed not to appear in the list. If that clicked instantly, you just learned a beautiful algorithmic trick. Why interviewers love this problem? It tests whether you can recognize construction problems, apply mathematical reasoning, and avoid brute force search. Strong candidates say something like, "We construct a string that differs from each input string at the diagonal index, ensuring uniqueness." That explanation signals deep algorithmic thinking. Similar pattern problems. This idea appears in Cantor diagonalization problems, constructive algorithms, and bit manipulation tricks. These patterns show up in Google-level interviews. This problem teaches a powerful lesson. Sometimes the best solution isn't searching, it's constructing the answer intelligently. By flipping the diagonal bits, we guarantee a string that cannot match any existing one. No brute force, no recursion, just one clever observation. And these kinds of insights are exactly what separate good coders from elite problem solvers. See you in the next breakdown.